So today we are going to deal with the equilibrium of forces, that is to be specific coplanar forces. So under coplanar forces, right? So this topic, right? So we have already done with the, in case of three different forces, then actually what is the equilibrium condition? The conditions are same, but actually in case of multiple forces, actually, is there anything specific actually that we can learn, so that we are going to deal with today? So there is one theorem called, so note down this theorem. Any system of coplanar forces acting on a rigid body is equivalent to a single force acting at an arbitrary chosen point, together with a single couple. So this is one fundamental theorem in case of coplanar forces. So the understanding here it is, so the problem that is coming with this kind of cases, suppose if there is a single force, then actually we can so straight away say that because of the single force there can only be a linear motion, right? So with only one force there is no possibility of equilibrium of the body. Now if there are two forces, then actually depending upon the scenario, if the forces are one opposite to the other, then actually there is no, so if provided if there is no difference between the forces, in that case actually the body is under equilibrium condition linearly. Suppose if the angle of operation of these forces on the body is different, then there might be a chance that actually, so the rotational motion also can come in, then we can say that the body is not under equilibrium condition. So to assure that the body is under equilibrium condition with many forces, or actually to be specific, if there are two different forces so that are acting on this particular body, then for that actually we built the rules, two different rules. One is the resultant force R should be equal to 0, and the other is M should be equal to 0, which is nothing but the moments of all the forces together about any random point has to be 0. So these are the two different conditions for the body to be under equilibrium condition. Now actually, if there are multiple coplanar forces, then actually for each and every force we have to assure the equilibrium condition, right? So if there are two forces, there might be a chance that there can be a rotational force. Then we have to assure that M is equal to 0. Now actually which two forces you will take out of all? Now for that understanding, or actually to clarify the confusion on that, there were certain theorems that got derived. So those theorems are, so one theorem is this one. So this one, any system of coplanar forces acting on a rigid body can be brought into a simple form called with a single force acting at a single point along with a couple. So this is how actually you can derive it. Now actually mathematically we are going to prove this how it can be. So one force is acting at this point, another force is acting at this point. Now actually we are saying that these two forces together actually can be brought into a single force which is acting at a single point, not at two different points of this particular body. So this is a randomly chosen point. So how it can be? Can you try to imagine? These two forces can be brought into a single point operation. So this is acting at this point and this force is acting at this point. These two can be brought together into a single point. So that's what is the statement, along with a couple, right? So here actually if there are multiple forces that are acting on a body at different locations, then actually we will take one force. Suppose actually if there are three different forces that are acting on this particular body. Now this is the XY coordinate system or the Cartesian coordinate system. Now I have taken a random point at this particular location. So this is a random point. Now actually if I draw this particular force, let us say it is acting at a location called A1. Let us say this is A1 location and it is acting like this. And this force at A2 location, it is acting upward. Let us say, so this is A2 location. And at this one, let us say this is acting at this particular point and this is A3 location. Now three different forces are there and these are operated at three different locations on the body. Now this can be brought together into a single force acting at a arbitrary location chosen. So here actually this is the arbitrary location. Now here actually what I will do is, this force I take it and this force I will take the exact magnitude of this particular force along with the direction of operation of this force and try to draw a force at this particular location. So that is at the origin, I draw the force F1 and I draw the opposite force to this, that is F1. So these two forces, one opposite to the other, but is having a magnitude of this one, which is F1. And then I have given the operation of the force is this one. Now here if you notice, these two together will cancel out. Obviously, right? So because actually equal magnitude acted opposite direction. Now these two forces together can cancel out. Now if I take the system of these three forces, so here actually opposite forces with equal magnitude here, and this is one force which is the original force which is acted at this location. Now if I notice carefully, so this force, let us say I call this as F1 or F11 and this is I call as F12, where F11 and F12 are equal in magnitude but of opposite direction. Now these two together, F1 and F11 will form a couple, right? Yes or no? F1 and F11. So these are actually equal magnitude, parallel to each other and one opposite to the other. Obviously these two will form a couple, right? That is the nature of a couple. So we proved that. So if two equal forces opposite direction, then it can form a couple. So that couple is this one. So this couple, I call this as M1, is this couple, along with a single force which is acted at this location. So this is F12 is this particular force. That means this can be divided as, at this particular location, one force acting at this location and along with a couple. So here actually this is the couple. So together will form the couple. And this is the force F1 which is the resulting force. So this couple plus this force together can be replaced for this particular one. Got it or not? Understood or not? Any question on this? Because the understanding of this is very important. Okay, great. Now take one more force. Yeah. So take one more force. If we take the second force, this force if I take it, and for this particular force, so exactly at the same location, I will draw a force which is parallel to this one and opposite to that again at the same location. Now this is going upward and this is going downward. These two together will form a couple of moment M2 and there is a resulting force that is acting at this location, which is the same location what we have selected for F1, and this magnitude is F2. And again if I take the third force, even for this also at the same location, I can draw two opposite forces like this, and then these two will form the couple and this one will be the resulting force of F3. So this couple is M3. Now, for all the three forces together, we have actually three individual couples along with three different forces, but the forces are acting at a single point O. This is a randomly chosen point. There is no fixed rule to select this. So, at an arbitrary chosen point where you can simulate as if like all the forces are acting at the random position like this, along with the corresponding couples, both will have the same effect. So this is the fundamental rule. Got it? Understood? Right? Okay. So you can note down this. This is the theorem. Actually, so if you take the sum of all the forces which are acting at a single location, you can straight away do the vector sum of all the forces. So if there are multiple forces like this, so all the forces together, this is F1, this is F2, and this is F3, and this is a randomly chosen location. And let us say this is the coordinate system, this is x-axis and this is y-axis. So this location is the point of action of this particular force, and let us say this is A1 and this is A2 and this is A3. So A1, A2, A3 are the position vectors. So let A1, A2 and A3 are the position vectors of the forces acting on the body. And this is O. Let O be the randomly chosen point. Randomly chosen point. Then all the forces can be replaced with a single force acting at O and will be R equal to F1 plus F2 plus F3. So if there are multiple forces, then actually it can be till Fr. Got it? So or else actually this can be replaced as sigma R equal to 1 to N Fr. So this is nothing but the capital R, which is nothing but the resultant force, and this force is acting at a single point O out of all these forces together, combined effect. Got it? And similarly, the couple, each and every force is having a couple. Now, if multiple forces are having couples, then the resultant moment will be the sum of all the moments together. That's what actually we proved in the previous class. So that one. So M is equal to A1 cross R1, sorry, A1 cross F1 plus A2 cross F2 plus A3 cross F3 plus dash 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 AR cross FR. This is nothing but the resulting moment. So this is the moment of all the forces together, and then this entire system can be replaced with this R and this M. Got it? So this can be in short form, you can write this as M is equal to sigma R is equal to 1 to N AR cross FR. So the system of forces can be replaced with R and F, R and M. Yeah. You can note down this. So this is the base rule to understand the equilibrium of forces in case of coplanar nature, because we are going to deal with multiple forces. If it is one force, you can straight away make out the system is not under equilibrium. If there are two forces, then you can simply calculate the resultant force and the resultant moment, and then actually you can assure that the equilibrium nature is there or not for that particular system. If there are three forces also, that also we have done in the previous classes, how we can do simply. But if there are multiple forces, then the complexity comes, because each and every moment you have to calculate and each and every force you have to calculate, and they are acting at different locations. That is the complexity. So because it is acted at different locations, then the complexity goes very high. In such cases, is there any special tools that we can use to understand the equilibrium nature of the body or not? So in that, one fundamental tool is what we have learned now. Now actually based on that understanding, there is one fundamental statement, that is the necessary and sufficient conditions. Necessary and sufficient conditions for the equilibrium of a rigid body under the action of a system of coplanar forces acting at different points of it. Or that the sum of those resolved parts of the forces in any two mutually perpendicular directions vanish separately and the sum of the moments of the forces about any point in the plane of the forces vanishes. Fine. So this is the statement or the necessary and sufficient condition for the equilibrium of a body in any case. So this is a generalized statement, and this is valid for whether the force is a single force, two forces, three forces, or 100 different forces also. This statement valid. So, but to summarize this, actually what it says is R is nothing but 0 and M is also 0. Then the system is equilibrium. So this is the statement. So this simple statement actually with all the necessary conditions actually he stated like this. Now actually to assure that R is equal to 0, the simplest way is even if you have 100 different forces, then every force can be made into two different parts which are perpendicular to each other, and those forces along x-axis and y-axis is usually the standard convention for any force to resolve. Suppose if I take actually one force is acting like this is F1, then the horizontal component of the force is F1 cos theta and the vertical component of the force is F1 sin theta. Now if I have one more force like this, and let us say this is F2, then the horizontal component will be F2 cos theta 2. Earlier this is theta 1. And this is F2 cos theta 2 and the vertical component will be F2 sin theta 2. Like this actually, if there are 100 different forces, you divide that into the horizontal component and vertical component, or the component along x-axis and the component along y-axis, which are perpendicular to each other. Now, if the sum of all the individual components along the x direction and the sum of all the individual component of the forces along the y direction, individual if it vanishes, then we are definitely sure that R is equal to 0. That means, so R is nothing but F1 plus F2 plus dash 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 Fr. This can be stated as F1x plus F2x plus F3x plus dash 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 Frx plus, and this is along x-axis. So that's why I multiply with I in the vector format, plus j times of F1y plus F2y plus F3y plus dash 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 Fry. So this is the resolved components along x direction, along y direction separately I have treated here. Now individual components are added along x-axis, individual component added along y-axis, and this can be replaced with capital X into I plus capital Y into J, where capital X is this one and capital Y is this one. Got it? Now, if the system is under equilibrium condition, after dividing this into x component and y component, x has to be equal to 0 and y has to be equal to 0. Then only we say that the system is under equilibrium condition. So this is only for the assurance of the linear equilibrium. But circular equilibrium can be stated only with the help of movements. So for now actually we can state that x is equal to 0 and y is equal to 0 is the necessary and sufficient condition for the linear equilibrium. For the circular equilibrium, m is equal to 0. Now actually this one also we will derive in terms of xy. So first you note down this. Done? Okay. Now, for the m to be equal to 0, so m actually we have defined as AR cross FR, sigma R is equal to 1 to n. So this is the moment, right? So this is the position vector and this is the force vector. Now these two actual cross product has to vanish 0. So this one we will write in terms of the x component and y component. So AR can be treated as the XR into I plus YR into J. So this is the position vector, because so if you say that the force is acting at this location in this direction, this position vector is nothing but AR can be treated as XR into I plus YR into J. So this is the position vector. This vector is the position vector. Got it? So this position vector you can always write Xi plus Yj. Now the resultant force component, or actually for this particular force, if I say this is Fr, then Fr can be treated as Xr into I plus Yr into J, where capital X and capital Y. So difference you have to notice it. Now the cross product for Xr plus Yr, where Fr equal to capital Xr into I plus capital Yr into J. So this is Fr. So if you do the sum of these two for R is equal to 1 to N, and this is what is M. So this M actually has to be equal to 0. Now this one, if you do the cross product of this is I and J. So I cross I will be 0 and I cross J will be K. So that is XR into capital YR, and then so I cross I is 0, I cross J is K. I take it common out, this K value, or I'll keep it here. So YR into XR, YR into XR, and J cross I will be minus K. And then J cross J will be 0. So this is the resultant cross product. So I cross I is 0, I cross J, K, and so this is J cross I is minus K and J cross J is 0. So only two factors will be there. Now here XR into YR minus YR into XR into K. So this is sigma R is equal to 1 to N. This is M. So this is the movement of all the forces together. You can express in this particular format depending upon the number of coplanar forces that are acting at this location. Now for the equilibrium of the body, this M has to be equal to 0. So M has to be equal to 0, and this K is actually the Z direction. So in this particular case it is the Z direction because you divided all the vectors into X component and Y component, assuming that all the forces are coplanar and are there on the XY plane. So with that assumption actually we have done. So assumption meaning the XY directions you can always treat on the coplanar or on the plane of the system, right? So that's why actually it is perpendicular to the plane of the forces, because all the forces are coplanar here. Now with this understanding you can ignore this K, because actually K is only one direction. So sigma R is equal to 1 to N and XR into YR minus YR into XR is equal to 0 is the necessary and sufficient condition for the system of coplanar forces to be under equilibrium. So only two things we are verifying. The sum of all the forces has to be equal to 0 and the moments of contributed by all the forces together has to be equal to 0. Got it? But in a more systematic manner, for many number of forces which are coplanar in nature, we have derived the conditions. So this has to be equal to 0 and X has to be equal to 0 and Y has to be equal to 0. So where capital X is the sum of all the force components along X axis, Y is nothing but the sum of all the force component along Y axis, and here individual moments actually we have calculated and added it together and everything sum up to 0. Then only we say that these three things will decide whether the system is under equilibrium condition or not. Got it? Any questions on this? Any questions? Okay, great. So you note down this. Find the equation of the line of action of the resultant. Find the equation of the line of action of the resultant of the system of coplanar forces system of coplanar forces acting at different points of a body. Acting at different points of a body. Now here, so the line of action of the force. So in the previous class actually we have derived, like actually, so there is a triangle and then actually BD is equal to 3/2 times of BC. In a triangle we proved earlier, saying that if there are three different forces that are acting on a triangle, the resultant line of action is somewhere here and which is perpendicular to that. So this is what actually we proved in the previous class. So now actually we are generalizing that statement. If not, so this is actually only the case of only three forces. But what if there are 100 different forces? Then actually how can we find out the line of action of the force here? So, so is there any systematic way of finding that? So because actually there actually we have taken all the geometry relations and found the angles and everything, and then it finally concluded that this is the line of action where this is located at a distance of 3/2 times of this particular distance. So that's what actually we proved. Now actually, so this is a generalized statement. If there are multiple forces, so where is the line of action of the force? So now actually to understand this, earlier actually based on the previous theorems, whatever we have proved, so we can conclude that if there are multiple forces, all the forces together can be converted into a single force acting at a randomly chosen location and then along with a couple. Now see this. So this is actually, let us say this is the resultant force of all the forces together. So this is the resultant force. Let us say this is passing through this particular point. This is nothing but the line of action of the resultant force. So, and we need to be finding out this particular line equation. So that is nothing but the line of equation of the force. Now, for this actually what I will do is, I will draw two different vectors of the same magnitude at the origin, but opposite direction. So this is R and this is also R, and this is minus R I call. So I have drawn two different forces at the origin, and the system of all the forces together, let us say it is resolving into a single force which is acting at this particular location of magnitude R. Now about this particular point actually, if we take the moments of the force, so this is the only force actually that is active because these two will cancel out and it is passing through this. Now if you want to take the moments of the force, then actually extend this line and then try to draw a perpendicular to this. So let us say the perpendicular length is P. Then if this is perpendicular distance, so this is the perpendicular distance P. Then the moment of your force is nothing but the force getting multiplied by the perpendicular distance. That means M is equal to P into R, or P is equal to M by R, where M is the resultant moment. So there is one more theorem. So if there are multiple forces and those forces individually contribute to the moments of M1, M2, M3 dash 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 up to Mn, then the sum of all the moments together will be a single moment, right? So that moment actually is equal to the moment of the resultant force. Got it? About the same point. So this statement actually we proved in the previous class. Now here actually let us say this is at a distance of A. This is at a distance of A. This R is actually passing through along, so on the x-axis it is cutting at x is equal to A. And then this R actually, if I divide this into two different components of the force, let us say capital X is the horizontal component and capital Y is the vertical component of the resultant. And then this resultant is passing through a point on x-axis where x is equal to A comma 0. So this is the point of A comma 0. Now if it is passing through this, then the moment of the force So moment of the force is same, right? So the moment of the force, actually you can say that this is A cross F, right? So A is this length, and then this vector I call this as AI. So AI is the vector. So A is equal to AI is the vector. So if I say this is the radius vector, and this radius vector for this particular force, the moment will be M is equal to AI cross R, right? So this is the M, and the same value is even equal to M is equal to PR. It will be the same, and then this R can be written as Xi plus Yj, because capital X is the force component along x-axis and capital Y is the force component along y-axis. Now, if I do the cross product of this, so M is equal to Ax into I cross I plus Ay into I cross J. So I cross I will be 0, M is equal to Ay into K. So this is the moment. So if you take the magnitude, M is equal to Ay or A is equal to M by Y. This is how you can write the magnitude. So here actually the resultant force is passing through a point where A is equal to M by Y, which is the point along the x-axis. So with the known values of M by Y, actually you will be able to express where it is passing through. But actually we are still not sure with what angle it is passing through. Now actually we can find out the equation of this particular straight line. So for that actually you have to understand the vector equation of a straight line. So I hope you people are aware of what is the vector equation of a straight line. Can somebody tell me? At +1 standard actually you might have learned. What is the vector equation of a straight line? Okay, so let me give the idea of vector equation of a straight line. Suppose if there is one vector A like this and there is one more vector B like this. Now the vector equation of the straight line along B and passing through a point with a vector tip of A, this straight line equation can be treated as, so this is the straight line equation. For this straight line actually you can calculate at any instant the R vector. R is nothing but Xi plus Yj, and this value is equal to vector A plus some random value T multiplied by this B. So this is the vector equation. So R is equal to A plus TB is the vector equation of a straight line. So this is what you might have learned at +2 standard or +1 standard. Here actually this is not complex. Let me explain why it is. See this. So this is A vector and this is B vector. Now the sum of these two, A plus B, is equal to R. So which will give you a random point at this location. Now if you want to identify a point at this location, what you need to do is, the location of this one is, let us say x1 comma x2 is the point, x1 comma y1 is this particular point, then the position vector of that particular point is nothing but the equation of straight line for us. So equation of a straight line is nothing but you have to tell the each and every point on that particular straight line with the known values. So here actually on this particular line you should be able to identify each and every point uniquely. So that value you will be able to find out with this R vector. So if you want to identify this point, this is the R vector. If you want to identify this point, this is the R vector. If you want to identify this point, this is the R vector. If you want to identify this point, this is the R vector. So this R value is nothing but as if like our xy relation, y is equal to mx plus c, where y and x are the variables, where the relation actually will tell you clearly where all the points will come in. So here actually this vector equation will give the complete relation where all the points will come on this particular line. So that relation is exactly the same as this one. So y is equal to mx plus c as equivalent as that of y. So R is equal to A plus TB is nothing but the vector equation of this straight line. Here this T is a parameter. parameter why we are putting this t is, suppose if I want to identify this value, the b vector is ended at this particular location. Starting from here, it was ended here. Now, if I want to identify a value which is after this b vector, then I need to multiply the b vector with a certain factor which is more than 1. So here actually if I want to identify, I have to identify a vector along b, but magnitude is more than b. So I have multiplied with a number called maybe let us say 1.2 or 1.3 or 1.5 like that. Now if I want to identify a point at this location, I will be multiplying the b vector with a magnitude which is in between 0 and 1, so that I can get a value of the vector till this particular point, because I have multiplied with let us say 0.6. So, and then this vector plus this vector together will be as per the triangular law of vector addition. This will be the vector resultant vector. So this resultant vector will give the point location of this particular point. If I multiply b with t, which is equal to 0.6, and adding this to a, so a plus 0.6b will be this point, a plus 0.5b will be this point, a plus 0.2b will be this point, and a plus 0 into b is nothing but the a vector itself, and a plus 1 into b is nothing but this point, and a plus 1.5 into b is this point, and a into 2 into b is nothing but this point. Like that actually, if I multiply with a bigger number, I keep on move on this line, and if I multiply with a 0 to 1, I will be starting from here and moving. Suppose if I wanted to have one more value which is on the other side, then actually I will be multiplying a value which is less than that. That means this value may be a minus b, because actually b is inverted on this direction. So a minus b into, so minus b into some constant. So that is maybe 0.1, let us say. So it keeps on gives the values on this particular one. So this position vector at any point will give the point on this particular straight line. So this position vector is nothing but the straight line vector, which we usually treat as r, which is equal to xi plus yj. Got it? So this is how actually you can find out the value. Got it? So the same equation actually we are going to use in this particular case. The same value, what we are going to use it here for identifying this particular straight line equation is, you know that this vector is the r vector, you know that this vector is a vector. So the equation of the straight line is nothing but, so r is equal to ai plus t times of r. So this is the equation of the straight line. Got it? So you understand this. So you note down this, then actually we will bring this into the normal known values of the resultant component along x-axis, resultant component along y-axis, and the moment values. So this straight line equation I will bring into those variables. First you note down into this one. This one actually moment of this particular force, right? So out of all the forces, you have brought into a single force, right? By adding up all the forces together, which is a single force, which is equivalent of all the forces acting on that particular body, and that is this one. Now actually, we have taken the moments of this particular force, or actually, we wanted to find out the moment of all the individual forces together. So as per the theorem, actually individual moments of all the forces together will be equivalent to a moment of a single force, which is equivalent to all the forces together. Now we are trying to identify the moment of the force, this particular force, about this particular point. So this can be done in two different ways. One way is, if you are able to find out the perpendicular distance between the point and the straight line equation where the line of action of the force is passing through, and if this is, so this is the perpendicular distance, then the multiplication of the force into this perpendicular distance will be the moment. The other way of finding out any random vector, suppose if you take this vector or this vector or this vector, even then also you will be able to find out the moment by doing a cross product of this vector multiplied by this particular force. So this force and this position vector, the cross product will give again the moment. Got it? So I hope you understood, right? R is equal to OR. So no. So R is the resultant force. So this is as if like F, but it's not the position vector. Position vector is, in this particular case, it is A. Got it? AI is the position vector. Now R is nothing but a random value on this particular line. So as I told you, this straight line equation in vector form, you can identify as R is equal to A plus TB, right? So R is equal to A plus TB is a straight line equation in Cartesian plane in the vector form. It is as if like y is equal to mx plus c. So y is equal to mx plus c and r is equal to a plus tb is one and the same. T is a parameter in this particular case. With two different vectors, you have constructed a straight line equation. Now, even here also, I wanted to construct a straight line equation which is passing through the force vector. So this straight line vector, I can identify with two different values, two different vectors. One is this position vector getting multiplied by this vector. So this will give the straight line equation like this. So this straight line equation is nothing but, if I draw a line like this is nothing but the r vector for us. So this r can be, so it will be a variable. So this r can be this way, or this r can be this way, or this r can be this way, or even this also r, or this also r, and this is also r, depending upon this parameter value. Got it? Understood, Vishal? Okay, so this is a straight line equation, that's all. Now this straight line equation in vector form actually we are bringing in. Now that too actually with the known values. So known values are actually, we have only the known values, we know only the forces. And those forces actually added up together to a single force called R. And that was divided into x-axis and y-axis. So x directional forces is x, and y directional forces together actually is added up to a single force called y. Now this R also we will bring into the known values. And then actually we will try to identify in terms of x, y and m the straight line equation now. Right? I hope you noted down this. So do you have any questions on this? So A is equal to m by y, actually this was already proved. And then another equation what we found is the straight line equation R is equal to ai plus t times of xi plus yj. Capital X is nothing but the force component along x-axis, and capital Y is nothing but the force component along y-axis, and this t is the parameter. This parameter will decide where the point will be. Now here, if you replace that, R is equal to xi plus yj. So this is actually position vector. Small x and small y are the position vectors, and capital X and capital Y are the force vectors. Got it? Plus t times of capital X into I plus capital Y into j. Got it? So if you add this, x plus tx into I plus y plus ty into j. So this is equal to xi plus yj, or x is equal to small x plus tx plus y, and y is equal to small y plus ty. Got it? This will give the position vector. Sorry, so there is a mistake here. So this is R equal to xi plus yj, and the same value is equal to ai plus t times of xi plus yj. Now here actually xi plus yj is equal to a plus capital Xi x into t I plus t into y into j. So this is the horizontal component and this is the vertical component of the position vector xi plus yj. That means x is equal to a plus xt and y is equal to ty. So this is the position of the straight line at any random location for a specified parameter of t. Now, if you want to put it in the Cartesian form of the straight line equation from the vector equation, then actually you can eliminate this t by putting into the normal known values. So this is t equal to y by capital Y, and if I replace into that, x is equal to a plus capital X into y by capital Y, and this a value you can identify this as m by y. So x is equal to m by y plus x by y times of small y. So this is the equation of this straight line. So Don't you notice that this is actually y is equal to mx plus c format, or x is equal to my plus c format? Got it? So x and y are the known force components, and m is the moment, and yeah, got it? This is capital Y. Done? So this one actually you can further simplify also. Small x into capital Y minus small y into capital X is equal to m. This is the equation of the force of action. Got it? So this is the equation of the line of action of the forces. So you can remember this because actually in case if there are multiple coplanar forces that are acting on a straight, so on a plane, then actually the entire thing can be found with the help of this particular equation, that is the line of action of the force. The resultant force can be found by adding up all the forces together, by dividing into x component and y component, and then finding out the magnitude of that based on x square plus y square under root. And the line of action of the force can be found with the help of this straight line equation. So xy minus yx is equal to m. M is the moment, and capital X is the force component along x-axis, capital Y is the force component along y-axis, and small x and small y are the relations in y is equal to mx plus c. Got it? Any questions on this?